Grazie tante, buongiorno a tutti. This is about everything I can say in Italian. Much of the talk will happen on the board, so therefore the question, can you read? Yes. Okay. Good. Let's begin. This is a graph that I need as I go along. What does it show? Along the horizontal axis you see the thermal energy of the universe. We will have to say more about what this is supposed to mean, but the thermal energy of the universe, thermal energy in electron volts. Right? And on the vertical axis you see the time in seconds on the left side and accordingly the time in years on the right hand side. This is just to scale thermal energy against time, right? So that you know when I speak about certain energy scales in the universe, you know approximately of what time after the Big Bang we are going to speak. So you see the horizontal axis runs the wrong way around. It begins at a mega electron volt and it ends on the right side at an electron volt. And the time increases as the energy goes down. So you see a mega electron volt is reached at approximately 1 second after the Big Bang. And then later we will need approximately energies of around an electron volt, which you see, well, are reached a few 100,000 years after the Big Bang. We will see about that. Afterwards, the thermal evolution of the universe gets rather boring. Okay, now let me briefly begin with the following statement. Number one, there will be a total of 8 points. Right? Number one, Wiens Law. What does it say? It says that the wavelength of the maximum of the Planck spectrum times the temperature is a constant. So that's the temperature that is the only parameter that characterizes the Planck spectrum. Lambda max times the temperature is a constant 2.898 millimeters times Kelvin, and that's it. Okay. We had a question that relates to this statement, right? But I think this got solved in the meantime. All right. So this is a constant. What does it mean? As the universe expands, lambda max gets larger, of course, right? Because all the wavelengths are increasing by the same measure as the universe itself, or all the scales in the universe are increasing. So therefore, I'm going to rewrite this equation a little bit. I'm going to write lambda max times A. This is obviously the same thing as we had before, right? But now, lambda max times A, this is the wavelength of the maximum of the Planck spectrum increasing with a cosmological expansion. So you see, in order to save Wiens law, the temperature has to go down like T over A, right? In other words, the temperature as a function of the scale factor in the evolution of the universe goes like the temperature today, if you choose to set the scale factor to unity today, divided by the scale factor itself, right? So temperature today, 2.726 kelvins, and as you go back in time, the scale factor goes down, so therefore the temperature goes up, right? Yeah, and at this point we could stop the lecture and say, but that's how it is, right? The universe gets larger, the temperature gets smaller, all right. But what kind of temperature is that? What kind of temperature is that? I mean, we know from the measurements of the COBE satellite that the leftover heat radiation in the universe, right, the cosmic microwave background, does in fact have a Planck spectrum. It's not just a Planck spectrum, it's the best observed Planck spectrum that you have, including all laboratory measurements. All right, so the photons in the universe, right, by far the most photons in the universe have a Planck spectrum. And this is the temperature of those photons. But this does not mean that everything else in the universe, fortunately, this does not mean that everything else in the universe must have the same temperature. And you can see a very simple example. If instead of a photon gas which is expanding, right, which leads to this result, you take an ordinary gas, right, an ideal gas, for example, and you expand this adiabatically. Why adiabatically? Well, there is no other way than expanding a gas adiabatically in the universe, because if you wanted to have a heat flow into a volume of gas or a heat flow out of a volume of gas, that flow would define the direction, and this direction would violate isotropy. So in a homogeneous and isotropic universe, which we all very strongly believe in, there must be adiabatic expansion. All right, but how does it go? How does it go? Can you see this? Tutto bene? Benissimo? All right. One result of studying adiabatic expansion in the universe is that this quantity here, I'm not going to derive this because I have other things to do, but this is the law of adiabatic expansion, right? So the product of temperature times volume to the power of adiabatic exponent minus 1. This is a constant if you expand an ideal gas adiabatically, and for an ideal monatomic gas, the adiabatic exponent is 5/3. So this exponent here is 2/3. And the volume scales like the scale factor of the third power, right? So I can write the same thing as T times A to the third power times gamma minus 1, right? It's the same expression. So if you insert 5/3, you get that T times A squared is a constant. In other words, as the scale factor of the universe increases, the temperature drops like A squared. It's completely different from the temperature of a photon gas, right? So this means you can speak of the temperature of the universe as long as the photons and the gas are closely interacting and are in thermal equilibrium. Then you can speak of those two having the same temperature. Right? And then the cosmic microwave background defines the temperature of everything else. But as soon as the photons stop interacting with the gas, for example, because electrons and protons combine to form hydrogen, then the gas behaves completely differently. Right? The temperature of the gas then begins falling like the scale factor squared, right? Much more rapidly than the temperature of the photon gas. And then it doesn't make any sense anymore to speak of the temperature of the universe, because different things in the universe will have different temperatures. Right? So this means that as long as the photons remain thermally coupled, right, closely interacting in thermal equilibrium with the gas, the temperature falls like 1/A. Third temperature then makes sense to speak about. But then as soon as they decouple from each other, right, the gas cools much more rapidly than the photons do. All right, so that's the second message, right? If you think of the temperature of the universe, say what you mean, right? If you mean the photons, okay, fine, then you have a scaling law like that. If you speak of the temperature of a gas, then as long as the gas is coupled to the microwave background, temperature falls like that. Once it decouples, it cools more rapidly. Interestingly, right, this adiabatic exponent here, 5/3, is for an ideal monatomic gas. If you had a gas that consisted of molecules which have 2 atoms, right, then this could be either 7/5 or 9/7, right? And then the scaling behavior of the gas changes. But that's not the main point that I wanted to speak about. What I rather would like to spend most of my time with is the following thing. Do you know this? I guess you have seen this before. What is this? Right? This is the map of the temperature fluctuations in the cosmic microwave background, the map produced by the Planck satellite. And the idea is that we want to see when in the history of the universe this map originates. Right? I want to show you how we can easily calculate at what temperature this image arose and what time this means, right? At what time this map came into being. And as you will see, once we know how to address that, we can also speak about another kind of process, a very important kind of process in the early universe, namely the process of the formation of the light nuclei in the very early universe. And the universe, shortly after the Big Bang, was hot enough to drive the fusion of hydrogen into helium. And I would like to show you how you can calculate when this happened. And as you will see, we will use exactly the same methods for that. And that's the key point that I wanted to tell you. Right? How do you do this? What is going to happen? How can we calculate this? Okay, so there are the main reactions that lead to the formation of light nuclei in the early universe. Protons and neutrons form deuterium, right, marked with a D, and then you merge or fuse two deuterium nuclei, and you get helium-3 in this case. There's a whole chart on the right-hand side. What I wanted to show you with this is that if you want to go from hydrogen to anything else, like for example helium, you have to go through deuterium. Right? There's no other way. So we will calculate when deuterium fusion happens. Right? This is the main point. So we'll calculate two things. When does the universe recombine? In other words, when do electrons and protons combine to form hydrogen atoms? That's one step. And the other one is, once we know how to do things like that, right, we can also apply this to the fusion of deuterium from hydrogen. It's exactly the same physics. All right. Let there be light. I need to go to the blackboard. All right, thanks. Good. So what do we want to do? We want to study reaction equations like this, right? A plus B gives C. And back. Why back? Well, in the very early universe, you can fuse, for example, protons and neutrons to form deuterium. But if the universe is very hot, the deuterium will be destroyed immediately afterwards, right? So you go back and forth. What I want to calculate is, how can the physics tell me on what side of an equation like this I'm going to end? Right? On this side, where the two ingredients are separate, or on this side, where the two ingredients are joined. Right? This is the main point. Now, how do you fix this? It's very easy. Right? We have to minimize the energy. We have to minimize the energy that is related to this reaction. It's the free energy, the so-called Helmholtz free energy. F, free, right? Good. This is given by a very simple relation. It's the Boltzmann constant, Kb, the absolute temperature T, times the logarithm of what we call the canonical partition sum. Never mind what that is. The canonical partition sum just tells you how many possibilities you have to realize a macroscopic state of a gas with very many microscopic particles. Right? No more than that. I'll give you a formula afterwards. But for a reaction equation like this, A plus B goes over to C and back, this canonical partition sum is very easy to write, right? You calculate the number of possibilities that you have for a single particle of type A. You raise this to the power of the number of the particles of type A, right? This reflects the fact that you just multiply the possibilities for each particle, for all the particles together. But then you have to make sure that the particles are all indistinguishable, right? So you have to divide by the factorial of the number of the particles of type A. Okay, that's it. Now you do the same thing for B and C, and you multiply all these possibilities together. If you want, you can think of the partition sum just as a probability. You just multiply all these things together. And you do the same thing for all three types, for all three species of particles. Okay, that's it. That's essentially all we need. It's essentially all we need. Now, what do we need to do? We need to find the minimum of f. Or rather, we need to find the minimum of the logarithm of this canonical partition sum. The minimum with respect to what? Well, the minimum for variation of any of these particle numbers. Right? So, for example, I could ask, where's the minimum of this whole expression? If I play with the number of the particles A, right? Why can I focus on the particles A? Because, of course, all the other numbers depend on that. Right? As I change the number of particles A by 1, of course, the number of particles B has to change by the same amount, right? Because you always combine 1A with 1B. Of course, if you have stoichiometric coefficients here, then you have to take them into account, but this is simple enough. And of course, as the number of particles A increases by 1, the number of particles C has to decrease by 1. Right? So they are all connected to each other. So it is in fact sufficient to take the derivative of this whole expression with respect to just one of these particle numbers. And since A comes first, right, we take A. Good. There's not much space. Let me go over here. I think I can wipe this off, can I?
Not to turn it around, there's the backside.
Yeah, but I want to leave this. I can turn this around, yeah, that's true. All right. So I need the logarithm of z, right? And I think you believe me, if I take the derivative of f with respect to something and I set it to 0, I can equally well take the derivative of ln z and set it to 0. And it's just a constant prefactor. All right, so I want to say 0 has to be equal to the derivative with respect to any of these particle numbers. I just pick particle type A of ln z. ln z. Mm-hmm. How do we do that? Well, it's just a product, right? So I have a sum of logarithms. But then there are exponents. So what I get is, I will have to take the derivative of NA ln ZA plus NB ln ZB and so on. Right? Aha. These are all the numerators. That was the easy part. Now, of course, we will have to subtract the logarithms of all the denominators. Aha. This is what we have to do. Now, how do we do that, right? How do you take the derivative of the log of a factorial? You take Stirling's formula. Let me write this over here because there's some space left. Stirling says the log of the factorial of a number is approximately equal n times the log of n minus n. Of course, that's approximate. But plot these two functions and compare them. You will see, even for a relatively small number of n, this approximation is excellent. Aha, so let's take this. But now if I take the derivative with respect to n, what happens? I have to use the product rule. So this gives me an ln n plus n times the derivative of ln n with respect to n. But that's just 1 over n. So I get n plus 1 minus 1. Oh, sorry, ln n plus 1 minus 1. Aha. Well, that's nice. So dn ln n factorial is just ln n. Isn't that nice? Of course, right, this is approximate. But as I said, for the numbers of particles that we are dealing with, sorry for the mess that I'm creating, but okay. For the numbers of particles that we are dealing with, this is an excellent approximation. All right, so we can just proceed. Right? It's very easy now. So we know that 0 has to be equal to ln ZA plus ln B, wait. I have to take the derivative of NB with respect to NA. So this means by how much does the number of B particles change as I change the number of A particles? Of course in the same way, right? Because I need one particle B for each particle A. So d ln B with respect to d ln A, that has to be plus 1. Okay, fine, then I can proceed. How is this with number C, NC? Well, just minus 1, right? Because for any particle C that is formed, a particle A has to disappear. Okay, so this is why here comes a minus sign, ln ZC, okay. And now we have minus ln NA minus ln NB plus ln NC. Of course, the plus sign has the same justification, right? As I increase the number of particles A, I have to decrease the number of particles C by the same amount. This is it. That's all. Let's bring this in a different form. ZA, ZB divided by ZC equals NA, NB divided by NC. Right? That's the consequence of that. How do you get there? Well, you leave the ZC's on one side of this equation. You bring the n's on the other side. You exponentiate the equation. You are there. That's called the law of mass action, or in other words, that's what chemists call the law of mass action. And of course, physicists know it all that we are. We have a deeper justification for that. Okay, the law of mass action. This gets a yellow box. Law of mass action. Wonderful. If you tell a chemist that's the law of mass action, he will frown at you and so on, right? But because chemists usually don't know what a partition sum is. But yeah, let's speak about what a partition sum actually is. You see, this was point number 3. We need point number 4. Point number 4. Now we need to fix what a partition sum really should be. Right? Okay, let's do that. For example, what is set A? I give you a very simple formula. I give you a justification. If you want to calculate it, you have to do different things. But it looks like this. I'm going to explain this, right? Look, this is a very simple formula. Let's read it from the right. This is the volume that you have for the gas. You divide the volume that you have for the gas by lambda cubed, right? By a little volume that you attach to each individual particle. So this tells you how many possibilities you have to put the particle A into the volume A. What wavelength you assign to this particle, that's a different story. But for now, just imagine you assign a little box of size lambda A cubed to each particle, and then this is the number of ways, or the number of subvolumes where you can place this particle. So that's very easy, right? That's just a probabilistic factor. This here is the Boltzmann factor for the mass, where beta is defined as just the inverse absolute temperature scale, right? 1 over kBT. That's just a shorthand notation. And GA is the statistical weight. This tells you, for example, if the particle A has a spin of a half, then the spin could point up and the spin could point down, and then GA is 2. It's a number of ways that you can orient the particle. So that's a very easy equation, right? It tells you, all right, if the mass of the particle is much higher than the thermal energy, it's going to be suppressed. It tells you you have to take into account that each particle can have an orientation by the spin. And then it tells you how many of these particles you can fit into the volume V. Okay? And lambda is the so-called thermal wavelength. This is given by Planck's constant. And there's just this formula here. Look what this is. kBt is an energy. kBt is an energy. If you multiply this energy by a mass, you get a momentum squared. So the square root is just the momentum. Do you recall what this is? It's the de Broglie wavelength, right? So that just corresponds to the de Broglie wavelength of a particle, but with a momentum of the particle replaced by the thermal momentum, right? The momentum according to its thermal energy. That's all we are going to need, right? There's a way of formally calculating this, but we don't really need that. Okay, you see, we are at number 4. We have 8 points to go through, so we're making pretty good progress. All right. So we have the law of mass action. We have an expression for all of these partition sums. Now let's just use them, right? The rest is just an application of these two things. Let me turn this round. It would have been miraculous if it would have been clean meanwhile, right? This would have been great. All right, so number 5. Now we are going to apply this to the cosmic recombination process. Right? So instead of A plus B goes to C, we are going to specify this equation. We are doing the following thing: P plus E minus gives hydrogen, right? That's cosmic recombination. We want to calculate when is this going to happen, how long is it going to take, blah, blah, blah. Okay. Now it's all straightforward to do, right? We just need to use the law of mass action that we just derived from the principle of least energy. Right? So we need Zp times Ze divided by Zh equals Ne times Np divided by Nh. But now what do we do with these numbers? What do we do with these numbers? Well, first of all, we know that for any free electron, right, that is, for any electron that is still flying around without being bound into a hydrogen atom, we know that there must exist a free proton, okay? Because the plasma is neutral. Right? So Ne equals Np is just a straightforward condition for the plasma to be neutral. And you take the bound protons, you must find the number of baryons, and this must be a constant. Okay? Because wherever you have the proton, free or bound, there is a proton. Right? And if you just add them up, you must find a constant, which I call Nb, is the number of baryons. So you see, of course, all of these numbers are related, and therefore I can write Np, let's write Nh, right? Nh, number of hydrogen atoms, it's just given by the number of baryons minus, now I should subtract the number of protons, but this is equal to the number of electrons, so I just subtract the number of electrons, and now I have expressed everything that I need in terms of the number of electrons. Okay, so let me just write this. This is Ne squared, right, because the number of protons equals the number of electrons, divided by Nb minus Ne. Okay, now let's express this by a dimensionless number. Of course, the numbers of particles are also dimensionless, right? But okay, now we are going to introduce the so-called ionization fraction. What does this mean? It's the fraction of electrons which are still free. Okay, so how do I get them? Well, I define this quantity x. This is the ratio of Ne divided by Nb. Right? It's the number of electrons divided by the number of baryons that there are. And if x goes to 0, then all the electrons are bound. This is what we want to know, right? When does x go to 0? When does the number of electrons go down to 0? The number of free electrons, right? Because then I'm on the right-hand side of this reaction equation over there, then I know that recombination is over. And if x goes to 1, I know that all the available electrons are still free, right? That's the fully ionized state. So x will go from 0 to 1 or from 1 to 0. and we want to know where is it, right? Depending on the temperature, what is x? Right? This will tell us on what side of this equation we are going to be. That's the whole story. Okay. But if I insert this definition over here, then you see I can write this as number of baryons. I take this out front of the fraction, and I have x squared divided by 1 minus x. Okay? If you just imagine for each NE you insert x times NB according to this definition, you can write the whole fraction like this. Okay. What do we do about the left-hand side? Now we know the right-hand side. Left-hand side. All right, now we just have to insert the expression for the partition sums for all the particles, right? But we just use the expression that we had there. All right, so I'm beginning at this point, right? And I'll just insert the expression that we had for the partition sums. Okay, first of all, we need the statistical weight of the protons. What is this going to be? Well, protons are spin 1/2 particles, right? So the statistical weight of the proton is going to be 2. It can be either up or down, down or up. All right, same for the electrons, divided by the statistical weight of the hydrogen atoms. What is this? Well, if I have a hydrogen atom in the ground state, then the spins will just be oppositely directed, and the spin of the hydrogen atom as a whole will be 0. Right? And then the statistical weight of the hydrogen atom is going to be 1. So we have factor 2 times a factor 2 divided by a factor 1. This is a factor of 3.999 or something like this. Okay, then we have the exponential where the mass terms occur. Right? We had e to the power of minus beta times mass times speed of light squared. Right? So the rest mass energy of the particle divided by the thermal energy. All right, so we have to take minus beta m proton plus m electron minus m hydrogen times c squared. What is this? It's the mass, what is now in parentheses, right? It's the mass difference between the ingredients before and after. If I multiply this mass difference by c squared, what do I get? What is that? It's the binding energy. It's just the binding energy of the hydrogen atom. What is that? 13.6 electron volts, right? It's a number we know perfectly. So I know what that is. I call this chi. It's the binding energy. Okay, very good. So remember, the rest that we had, or the final expression that we had in the partition sum was just volume divided by lambda cubed. But now we have 3 times the volume, and we have 3 different lambda cubes, right? Okay, let's just insert them. So now I now have volume times, can you see this? Volume times volume divided by volume. This is pretty much volume. And now we have 1 over lambda p cubed times 1 over lambda e cubed times lambda h cubed, right? So lambda h divided by lambda p lambda e cubed. That's it. That's the left-hand side. But now the thermal, this thermal wavelength, right? These lambdas here, just depends on the mass and the temperature. The temperature, of course, is the same for all 3 of them. But the mass of the hydrogen atom and the proton are about the same, right? So lambda h and lambda p just cancel out. Isn't this nice? So that's all that's left, right? A factor of 4. E to the power of minus binding energy divided by thermal energy. And then this ridiculous factor there, right? Volume times 1 over lambda electron cubed. Okay, good. This is, well, this has to be NB times x squared divided by 1 minus x, okay? Now we massage this a little bit to find x squared divided by 1 minus x on the left-hand side. So I'm going to divide by the number of baryons, okay? But then you see I'm going to divide the volume by the number of baryons. The number of baryons divided by the volume, that would be the baryon density. Okay, so we get the inverse baryon density. All right. 1 over NB. All that's left is the thermal wavelength of the electrons cubed. Look how nice this is, right? This is the number density of baryons times a volume, lambda electron cubed. So it's the average number of baryons per electron volume. It's a dimensionless thing. Very nice. Here we have a factor of 4. Let's put it up here. And the rest is just e to the minus beta chi. Okay? That's it. That's it. That's all we need to do. This is Saha's equation. Yellow box. Saha's equation. Okay. Look, now what do we have to do? What do we have to do? On the right-hand side, all we have is constants, except for the temperature. Okay? The binding energy of the hydrogen atom is just 13.6 electron volts, number we can plug in. The number density of baryons, I will show you how to get this, times the electron wavelength cubed, when I showed you the formula for the electron wavelength, right? Also what enters there is just the temperature and the electron mass. All right, so the next step, step number 6, is just the evaluation of this thing for the hydrogen recombination. Okay. What's the time, by the way? Is there a clock? 11:45. So I'm supposed to run until 12:30, right? Very good. Very good. Let's have a break. No. Evaluation. What do I mean with this? I just want to evaluate the right-hand side. Now, I need a crucial number. I need a crucial number, namely the following thing. The number of baryons in the universe is related to the number of photons in the universe by a constant. Interestingly, the constant is called eta, or let's call the constant eta, okay, times n gamma. All right, n gamma is the number of photons in the cosmic microwave background, for example. There are very many. Right? There are 405 per cubic centimeter nowadays. Right? If you want, you can catch them here in the room and then take them home. Right? 405 per cubic centimeter. The number of baryons in the universe is much, much less than that. Interestingly, 1 over eta, right, which is much easier to remember than eta, is 1.5 times 10 to the power of 9. This is one of the most important numbers we have in cosmology. We do not know what set this number. This must be set by a process that controlled the number of particles relative to the number of antiparticles. Because then if you combine the particles with the antiparticles, you get all the photons. So this number tells you that for any baryon in the universe, left over in the universe, there must be 1 billion photons. In other words, for each 1,000,000,001 baryons, there existed about 1 billion antibaryons, and they all combined and left just photons. And 1 baryon out of 1 billion was left over. We don't know the exact physical processes that set this number, but this is one of the most important cosmological constants, right? 1.5 times 10 to the 9 photons per baryon. Let's accept this as a number, right? It's a different story how we get it, but this is what it is. Okay. But the number of photons you can easily calculate, right? You know from the Planck spectrum what the number of photons is if you have a temperature. Number of photons just scales with the temperature like the third power, and there are some constants. And now comes the trick. So you take the Planck spectrum, you calculate the number of photons per cubic centimeter or whatever it is, and you get the following result. It's 4 times square root 2 divided by square root pi. Okay, that's what a usual pocket calculator can do. Zeta of 3, what is this? That's Riemann's zeta function evaluated at the value 3, that's 1.202 times something. Okay, so that's just a constant you have to accept, right? It's just a constant like pi or whatever. All right, so this is 1.202 and so on. It's an irrational number. All right, the rest is just set by kBt divided by MEC square to the power of 3/2. I'm not done yet, right? I'm just combining numbers. So what is this? This is the thermal energy that you have at temperature T. And this is the rest energy of the electron, 511 kiloelectron volts. So this is also a dimensionless number. And now you multiply this by the thermal wavelength of the electron to the power of -3. All right. I'm just presenting your result here. But I think the way of getting to this result is very easy. Right? First of all, you calculate the number density of photons from the Planck spectrum. That's an easy exercise. Then you find the combination kBt in this formula, of course. And then you eliminate kBt to the power of 3/2 by means of the thermal wavelength. And leave the rest. And that's it. Why am I doing this? Because, of course, now I can multiply the lambda E cubed on the other side, right? I know you can't do this on paper, but that's my advantage. Okay. That's it. So you see, of course, this has to be a dimensionless number, right? It's just a number of photons in the volume set by the thermal wavelength of the electron, and this number here, which is set by the comparison of the energy scales, right? You compare the thermal energy scale to the rest energy scale of the electron, and that's all that there is. Okay. So now we have lambda E n gamma, lambda E cubed times n gamma. What we need is lambda E cubed times NB, but of course there's just a factor of eta in between. All right. Sorry, I need this. So I turned this around even though I just wrote it down. But I think you also did you? If you didn't, it's your fault. All right. All right, so what do we have now? What do we have now? Let me copy this over there. Right, I'm just beginning at Saha's equation again, but then I'm going to insert on the right-hand side all the results that we had. All right, so this is 4 times. Now I need NB times lambda E cubed, and I need this in the denominator. 1 over. What was this again? Okay. NB was eta times n gamma. N gamma lambda E cubed was 4 root 2 divided by root pi zeta of 3. These were all the constants. Now comes the temperature factor. Right, this I'm going to write as MEC squared divided by KBT to the power of 3/2. Okay. Of course, it looked the other way around, but I now have to put it in the denominator. And this is e to the minus beta chi. Right? That's it. This is very easy. Why? Well, these are just numbers. All the energy scales we know once you set the temperature. Right? Once you set the temperature, kBt, you know all these numbers here. Okay? So this here is just a function of temperature, and you can easily calculate it. Right? It's e to the minus function of temperature divided by temperature to the 3/2 power. And I call this Fe for electron of T. Okay? Now what do you have? A quadratic equation. Right? That's easy to do. X squared equals 1 minus x times Fe of T. Okay? That's a mixed quadratic equation. You can easily solve that. It has two solutions. One is senseless because it gives you a negative ionization fraction. The other solution is the one that you need. And you get a mixed quadratic equation for any temperature you set. So what do? You fix a temperature, you know this number, you solve it, you get x. Now let me show what happens. Look, this is this function Fe of T. Look what happens. Again, the horizontal scale goes from 0 to 100 electron volts. Why did I do that? Well, of course, for one reason, right? The energy scale of the hydrogen atom is 13.6 electron volts. Right? So I wanted to have a bit below and a bit above 13.6 electron volts. So I'm going from 0 to 100 electron volts. Look at the values of this function f. Right? It goes up to 4 point something times 10 to the 15. Well, who ordered that? Look, I mean, x must be between 0 and 1. So set it a half. Then you have a quarter divided by a half. Right? That's pretty much a half. So in order to solve this equation, Fe must be of order unity. But almost everywhere it's of order 10 to the 15. Did we do anything wrong? No. No, look, it starts at 0. At the lower left corner, right, it shoots up like a rocket. So we have to go very, very close to energy 0. This is interesting. All right. If I solve this equation, and I told you, right, it's just a quadratic equation that you need to solve, then you get this ionization fraction here as a function of thermal energy. And you see the horizontal axis scales from 0.2 to 0.4 electron volts, very much smaller than the 13.6 that are set by the energy scale of the hydrogen atom. Then you see, okay, it goes up from 0 to 1. Of course, in the cosmic history, it goes from 1 to 0. Right? So we are running from top right to bottom left as the universe expands, cools down, energy drops, ionization ratio goes down from 1 to 0. In other words, hydrogen forms. All right. And you see it forms at around 0.3 electron volts. Why is that? Very much at very much lower energies than correspond to the binding energy of the hydrogen atom. Well, this is of course because for any baryon in the universe you have 1 billion photons. So you have to supercool the photon gas in the universe before hydrogen can really combine, because otherwise, if you have 1 billion photons per baryon, even if you cool the baryon gas very much below the energy scale you are interested in the Maxwellian tail of the photon energy distribution, you will still have very many photons that can re-ionize the hydrogen atoms that just formed, unless you supercool the whole thing. Right? So you have to cool down from 13.6 further to about 0.3 electron volts, and this delays the recombination process of the universe by a whole lot. Right? This is what happens, right? The large ratio of photons to baryons. This is the reason why the whole recombination process is dramatically delayed. But you see how easy this all was, right? We just minimized the free energy, right? And used expressions for the partition sum for an ideal gas, and we get this out. Okay, now let us compare these two time scales. Right? Remember the graph that I showed you in the beginning, which just showed how energy scale corresponds to time scale. Now, of course, the energy scale is running the other way around in comparison to the graph that I showed you in the beginning. So the curve that was rising in the first graph is now falling. Right? So the blue curve gives you the time. The red curve now gives you the ionization fraction. And if you want, for example, the ionization fraction to drop to about, let's say, 10%, in order to say now it's almost over, right? Recombination is almost over, then you find, okay, this is at approximately 300,000 years after the Big Bang. This is one thing you see. There's another important thing you see. You see when it starts and when it ends. Of course, this takes a while, right? It begins at roughly 220,000 years after the Big Bang. It ends approximately at, where are we? Here we are, approximately 300,000 years after the Big Bang. So it takes a while for the universe to recombine. Right? The half-width of the time is approximately 40,000 years. So it's not an instantaneous process, right? It takes a while. This is also something you can read off this graph. Okay, so you see we have reached fundamental results here with very easy physics. All right, now let's apply the same ideas to primordial nucleosynthesis. And you will see this is equally easy, and you also will get some very important results. All right, I'm going back to the board. We have reached section number 7. So see this just as a second application of just the same laws, right? There's nothing, almost nothing new, almost. Okay. Now we look at nucleosynthesis. So I'm looking at proton plus neutron goes to deuterium and back. Of course, right, there are subsequent processes. Deuterium plus deuterium gives helium-3 plus a neutron, and so on and so on. But you have to go through deuterium, right? So unless you efficiently produce deuterium, nothing else is going to be produced. So that's what we calculate, right? This equation now. What's the first step? Well, the law of mass action, obviously, right? So Zp times Zn divided by D, right? Zd is what? Np Nn divided by Nd. Same thing as before, right? I'm just writing down the law of mass action, but now specialized to this particular reaction equation. But now we have a problem. There's a subtlety here. And I'm going to write this subtlety down on this board so that once you have seen it, we can hide it again, okay? The reason is the following. Of course, now I need to relate all these numbers Np and N and D and so on to each other. But now I have to be very careful in doing this. Np is the number of free protons, right? It's the number of protons not bound yet into deuterium nuclei. But now I can't use my neutrality argument anymore because the neutrons are neutral, as the name suggests, right? So I can't just say Np equals Nn. And it isn't. So we have to be careful about this. All right, but first of all, we know if I add the free protons and I add the free neutrons and I add twice times the number of deuterium nuclei, then I get a constant, right? Because that's just the number of baryons that are flying around. Okay, here is something we can write down. That's Nb. All right, very good. Now, the crucial point is this. If I take the number of number of free protons, and I take the number of bound protons, so these are the protons that are already bound in deuterium nuclei, then I get what? The number of all protons. Eh? Mm-hmm. But the number of neutrons is lower than that, for a reason I'm going to tell you. So I'm doing the same thing for the neutrons, okay? But this equation is not correct, because the number of neutrons is lower than the number of protons. So there's a factor r here, and the r is smaller than 1. Why is that? First of all, the neutrons are a bit more massive than the protons. So it takes a bit more energy to make a neutron than to make a proton. So if you fix the energy scale, there will be fewer neutrons than there are protons. That's one effect. And the other one is free neutrons decay into what? Into protons, of course, right? So both effects add together, right? The somewhat higher mass of the neutron and the neutron decay into protons both add up and make the number r smaller than 1. In fact, set it to approximately 1/6. So that's a constant. This is something we have to calculate from, for example, the theory of the beta decay and from the half-life of the neutron, right? What's the half-life of the neutron? It's about a quarter of an hour. Right? Okay. So this we have to take into account. Now what do we do with this? Well, this is the number of bound protons, as I said. Yeah?
I just wonder, is it really a constant, or doesn't it also depend on density and temperature and things?
It does. It does. But we can set this as a constant because the energy scales where this beta decay stops, for example, are much higher than the energy scales we are calculating. But it's an important point. Right? Let's just set it as a constant. If you wanted to have a precise calculation, you would have to take into account that this ratio changes with temperature as well. Yeah? It doesn't matter too much. All right, so that's the number of bound protons, but of course the protons are bound in deuterium nuclei, so the number of bound protons is exactly equal to the number of deuterium nuclei. Okay? Each bound proton is in a deuterium nucleus. And there's just one per deuterium nucleus. So this is the number of deuterium nuclei. Of course, same thing for this. Right? So the number of bound neutrons is, of course, also equal to the number of deuterium nuclei. Right? Because there's just one proton, one neutron in a deuterium nucleus. All right, very good. But then I can solve this for n, right, for the number of free neutrons, and I have eliminated another number. Right? So this allows me to say the number of free neutrons. Well, what is that? It's r times the number of protons. Okay. It's r times the number of deuterium nuclei minus the number of deuterium nuclei. So it's plus r minus 1 and d. Okay, very good. So we have eliminated one more number. Now we just need to eliminate the number of deuterium nuclei as well. And for this, we return with that expression into that equation. Okay? What happens? To NP, you add R times NP. So you get R plus 1 times NP. To 2ND, you add 1ND. Sorry, you add RND. You subtract 1ND. So you also get 1 plus R times ND. Okay? So, if you call this equation number 1, then using this result with equation number 1, you get 1 plus R times NP plus ND equals NB. Okay? I think the principle is very easy, right? You just insert this and so on. All right. But this now allows us to eliminate the number of deuterium nuclei. Okay, so from here you conclude that number of deuterium nuclei, well, you just solve for that, right, is Nb divided by r plus 1 minus Np. That was the result I was driving at, right? Because now I just have a constant, Nb, the number of baryons, and the only variable that I'm driving at, namely the number of free protons. All right, and now with this result, I go back into that equation, because then I will have an expression for the number of neutrons, number of free neutrons, right? Okay, what happens? So I have to multiply this equation by r minus 1. And then I have to add the result to that. So what happens? To r times np, I'm subtracting r minus 1 times np. So the r times np just drops out. And what's left over is just the np. Right? So I just keep writing here, right? So this is now np. And then, of course, we have r minus 1 divided by r plus 1 times the number of baryons. All right, now we have everything together. Now we can express all the numbers in terms of a constant, namely the baryon number, and a single one of the numbers of the species, namely the proton number. Okay, fine. With that result, we go back here. We need NP. Okay, that was easy. We need ND. That's that. Okay, we need to multiply. All right. NP plus r minus 1 divided by r plus 1 times NB. Okay, that's the numerator. Now we have to divide by the number of deuterium nuclei. So we have to divide by this number over here. Okay. So that is what? NB divided by r plus 1 minus NP. Okay, that's what it is like, right? Now, of course, the first thing we do is we extend this fraction here by r plus 1, right, to make this go, and that. But again, the board is too small. Let's continue over here. Right, so what do we have? Again, we have Zp, Zn divided by Zd. We deal with this later, okay? Let's just apply some cosmetics to the right-hand side. Okay, so that's Np times r plus 1 times Np. Remember, I'm extending the fraction by a factor of r plus 1. Okay, so this is why I get r plus 1 Np. Now, plus r minus 1 times Nb divided by Nb minus r plus 1 times Np. Aha. And of course, we play the same trick again now. Now we say, okay, the number of free protons divided by the number of baryons is called X now. Okay, it's the same procedure as before. Not the same procedures every year, but as before. And we get, what do we get? X times r plus 1 times x plus r minus 1 divided by 1 minus r plus 1 times x. Okay? Well, it almost looks like the result before, right? Just because r is not 1, but something different, you get some factors in there. All right. So with the right-hand side, we are done. Right? It's modified compared to our result for the hydrogen recombination because neutrons decay. But okay. What do we do with the right-hand side? Let's do it here. Statistical weight for the protons. 2, right? Protons also have a spin of a half. So I have 2 possibilities. Factor of 2. All right. Statistical weight for the neutrons. Again, factor of 2. Statistical weight for the deuterium nucleus. Well, okay. In the ground state of the deuterium nucleus, it's going to be, spin is going to be 0. So the statistical weight is going to be 1, right? So again, that's going to be a factor of 4. Then we have e to the minus beta chi, right? Like before, but now the chi is not the binding energy of the hydrogen atom, of course, but the binding energy of the deuterium nucleus. What is this? So instead of 13.6 electron volts, it's 2.2 mega electron volts. Okay, you just look up a table and you get it. All right, so that's the binding energy now instead of the hydrogen atom of the deuterium nucleus. All right, now what else did we have? We had, volume. Let's write it there. All right, now we have to use these factors for all the particle species. So I get again volume times volume divided by volume. That's this volume here. Now I get lambda d, so the thermal wavelength for the deuterium nucleus, divided by lambda p times lambda n, and the whole thing to the 3rd power. Okay? That's the left-hand side. Right? Let me just write equals. Right? Okay, now what? Now what? Careful. Lambda p, the thermal wavelength for the proton, and lambda n, the thermal wavelength for the neutron, they are approximately the same, right? Because the masses are approximately the same. All right, so what can we do? We can set lambda p approximately lambda n. Okay, what about the deuterium thermal wavelength? Well, it goes like 1 over the square root of the mass, right? The thermal wavelength. But now, the mass of the deuterium nucleus is just twice that of the proton. Right? So the thermal wavelength of the deuterium just is 1 over square root 2 times lambda p. And so lambda d approximately lambda p divided by the square root of 2. That's it. That's it. And then you see, all right, again, what we are left with is just one of these thermal wavelengths. We can use the thermal wavelength for the proton, for example. And all we get is a factor of 1 over square root 2 to the 3rd power. And that's 1 over 2 times square root 2. Okay? So instead of this factor of 4, we get a factor of 2 over square root 2 or square root 2. That's it. That's it. Let's continue over here. So we have reached point 8. Point 8 is again the evaluation of this thing. All right, again, lambda p divided by square root 2, lambda p. So 1 over square root 2 to the 3rd power. 4 divided by 2 square root 2 is 2 divided by square root 2 is 1 over square root 2. No, sorry, it's square root 2. E to the minus beta chi. Well, we know what that is. Chi is 2.2 MeV. And what we are left with is volume divided by thermal wavelength of the proton cubed. NB, all right, x r plus 1, x plus or minus plus r minus 1 divided by 1 minus r plus 1 times x, okay? That's it. Now, of course, we do the same thing as before, right? We divide by NB, we get 1 over the number density of the baryons. We relate this to the number density of photons. We split this up into temperature and what was it? Temperature and what was it again? Oh, anyway. So, what do we get? We get x times r plus 1 times x plus r minus 1 divided by 1 minus r plus 1 times x. I've just copied the right-hand side except for the NB. Okay. Now I get on the right-hand side the square root 2 e to the minus beta chi 1 over number density of baryons times proton thermal wavelength cubed. All right, so that was 4 times square root 2 divided by square root pi zeta 3. These are just the same constants as before. Now we have m proton c squared divided by kBt to the power of 3/2, okay? The only thing that changes is where before we had the mass of the electron, we now have the mass of the proton. What is that? It's about a GeV, right? Giga electron volt. All right. What else? Again, the ratio of the number densities, the baryons, and the photons, right? So this is now, again, as before, just another function of the temperature. Let's call it Fp of T, right? P for proton. Fp of T. All right? And again, we have a mixed quadratic equation. We can solve that, right? So it's a mixed quadratic equation now in x. And x is the fraction of free protons. But then again, right now the coefficients are more weird than before. But for every temperature you set, you know this number. We know what R is, namely 1/6. So we can solve this quadratic equation, right, like before. So that's this thermal function Fp of T, right? This is the right-hand side of this equation. Again, you see the same thing as before, right? But now the energy runs from 0 to 10 MeV. Right? Appropriate for nuclear physics, the energy scale is not electron volts, but mega electron volts. All right, again, you see that this thermal function rises up to about a few times 10 to the 12th. This is not what we need, right? We need F to be of order 1 to solve this equation. So again, we will have to go to the left, the leftmost end of this plot, right? So the energy must be much below, the energy where deuterium forms must be much below the binding energy of the deuterium nucleus for the same reason, right? For the same reason, because we have 1 billion photons per baryon to destroy the freshly formed deuterium nuclei, unless you cool the photon gas much below the binding energy of the deuterium. Right, so, same thing as before. Here's the plot. But now, I'm not plotting x. I'm not plotting x now. Rather, what I'm plotting is y. Why? Because I plot here np divided by np plus np prime, okay? This I define as y. This is the ratio of free protons and all protons. Okay, that's a number that's more easy to understand. That's the reason. All right, now you see it does not drop to 0 like the electrons did. Why not? Because, of course, there are so many protons than there are neutrons. And even if you bind up all the neutrons in deuterium nuclei, there must be a lot of protons left, right, who just don't find a partner. Right? Even with the internet, right? They don't find a partner. All right. So what happens is you start on the right side of this plot at high energies at a free proton fraction of 1, right? All the protons are free. There is no deuterium yet. All right, and then the energy goes down. We are moving to the left on this plot. And then deuterium fusion starts. And you see when the curve turns flat again, it's over. Right? Then all the neutrons are bound. And there are lots of protons over, but of course that's what it is. Okay, so you see at approximately 60 kilo electron volts, right? 0.06 MeV, about 60 kilo electron volts, the fusion of deuterium is essentially over. But the binding energy of the deuterium nucleus was 2.2 MeV. So again, the very high number of photons per baryon delays the effective deuterium fusion to approximately 60 kilo electron volts rather than 2.2 MeV. All right, what about time? Same plot as before. Right? Again, the dependence of time on energy, cosmic time on thermal energy of the photons in the universe. Right? This is the blue curve. And again, you see it starts when the universe is about 4.5 minutes old. Minutes! 4.5 minutes old. It's over when the universe is about 6 minutes old. So the universe had about 1.5 minutes. The universe. How old is it now? It's about almost 14 gigayears. Right? If you live long enough, you will live until the 14 billionth birthday of the universe. Okay. Now it's almost 14 billion years old. It had 1.5 minutes to convert hydrogen to deuterium, and then the deuterium on to helium-4 and so on. Right? What did it do in these 1.5 minutes? It converted approximately 240 grams of hydrogen into helium. Well, try this at home, right? I mean, in these 1.5 minutes, the universe managed, the universe was able to convert 1/4 by mass of the hydrogen mass into helium. And afterwards, as time went on, it was too cold. Earlier, it was too hot. 1.5 minutes. All right. Now, how do we know that this is correct? Well, we can ask how much helium is there in the universe. For example, you can have a look at the spectral lines in the sun, in the spectrum of the sun. You can measure by the equivalent width of these spectral lines how much helium there is. You find approximately 24% of gas by mass is contained in helium-4. Right? All right, that's what I wanted to show you. These are two very interesting epochs in thermal history of the universe. So let me summarize what happened. Right? What happened is the following. First of all, we saw that simply by Wiens' law, we know that as the universe increases, the temperature must drop by the same amount as the scales in the universe grow. Okay, so when the universe becomes linear scales in the universe become twice as large, temperature falls to half its value. That was message number 1. Message number 2, this applies to photons. It does not apply to gas if the gas is not coupled to the photons. Right? So neutral gas atoms are of course not coupled to the photons anymore, or at least very weakly coupled. And therefore, the temperature of the gas then falls much more rapidly with the expansion of the universe than the temperature of the photons does. That was message number 2. All right, and then we looked into distinct events in the evolution, the thermal evolution of the universe. One event was the hydrogen recombination, which gives rise to the release of the cosmic microwave background. The other one is the formation of deuterium in primordial nucleosynthesis. Both physically are the same thing. Right? You look at the reaction equilibrium of a reaction equation like A plus B goes to C. We derived the law of mass action. What was the foundation of that law? It's just the minimization of free energy. So from the law of mass action, when we applied this to recombination, we got Saar's equation. And we could derive that the energy scale when the cosmic microwave background was formed was about 0.3 electron volts. And this happened when the universe was about, well, the exact calculations has 380,000 years old. The whole process did not proceed instantly, but took about 40,000 years. Then we applied the same principles to primordial nucleosynthesis. And the only complication we had to take into account was that there is a ratio smaller than 1 between the number of neutrons and the number of protons, just because the neutron is a bit more massive than the proton, and it decays by beta decay into protons. Right, so we had to take this number into account. This made the left-hand side of this equation a bit more complicated, but the principle, of course, remains the same. Right? And then we saw, all right, nucleosynthesis begins when the universe has cooled down to approximately 70 MeV, 70 kiloelectron volts, 0.07 MeV, and is over when the temperature has dropped to about 60 keV. It takes about 1.5 minutes. All right. That was the simple message. Thank you very much. The only problem is the calculation is wrong. The calculation is wrong. Why is it wrong? Well, what we have assumed throughout the whole calculation is thermal equilibrium. Right? This condition that you minimize the free energy and get the right result, this assumes that there is thermal equilibrium between all the constituents that you have. But of course, as recombination proceeds, this is not true anymore. Right? Because as you form hydrogen atoms from protons and electrons, the free charges disappear. And the mean free path becomes very long, and thermal equilibrium breaks down. However, the result is nonetheless almost correct, because once recombination sets in, it's over very quickly. Right? It takes about 350,000 years until it starts. It takes about 40,000 years to end. So the time that recombination takes is about 10% of the time of the age of the universe when it starts. And because recombination is so fast, also because nucleosynthesis proceeds so fast, this thermal equilibrium calculation is very, very close to the real result. So keep in mind, it's strictly not correct, because we fall out of thermal equilibrium while we apply this equation. Nonetheless, that's the principle of the calculation, and the result is almost correct, and it's very easily derived. Right? That's what I wanted to show you. These are these two epochs in the thermal evolution of the universe that I wanted to show you. Thank you very much.